To start out section 1.6 on linear approximations and the tangent line, what I want to do is just give you a visual of what this section entails. So the big picture here is this, and there's a lot of notation in this section, so I don't want you to get lost in that. But the idea is this. Let's say we've got some curve. So let me go ahead and draw out. Here's my axis systems. So here's the x-axis. Here's the y-axis. And let's say my curve looks something like this. Okay, so this is f of x. That's the curve there at any x value. Okay, now what I want to do is I'm going to take an arbitrary point. Okay, so let's take this guy right here. Now I'm going to use the notation that they're using right here for you. Okay, but you don't have to use that. Okay, you can use any other. You don't have to use x sub naught. You could use like the letter c or something. So here's what they're saying. Let's say I pick some arbitrary point. Okay, and it also then it has a height of f at x naught because that's the function. Now let me go ahead and draw in a tangent line here. I'll do it in green still. So let's just eyeball in the tangent line like that. And now let's say we take another point over here. Okay. I don't know where this point is. Let's just say that it's over some distance delta x. So this guy right here is x sub naught plus delta x. So if I go up here, the actual height of the function right here, the height of the function is f at x naught plus delta x. And that's what this height right here is. Now the big picture is that this tangent line is relatively close to this point. And the smaller delta x is this way, the closer this blue point will be to this green line. So what we're saying is that this distance right here, okay, so this distance is going to be smaller as delta x goes to 0. So as delta x becomes smaller, if we push that point in, the distance between the white line and the green line gets closer and closer. So the tangent line becomes a good approximation to the actual function. Okay, and is only with small delta x's. So as delta x is super small, this line right here becomes a good approximation to this line right here. That's what this is saying up here, but it's not as obvious maybe as what you think. So what I'm going to do is I'm going to show you this piece back over here. Okay, so this guy right here, this point, let's get an ordered pair for that point. Okay, well, what do we know? We know that the slope, let me go like this. We know that the slope of this green line, the slope of the green line, is given by dy dx, or f prime of x at x naught. So if I take the derivative of the function at this value right here, it gives me the slope of this line. So that's this guy. Now if I want the equation of the green line, then I've got the following. I've got y minus y1 is equal to m times x minus x1. Well, I need a point on my line. That's the y1 and the x1. Well, I have a point on my green line. Here it is. So let's go ahead and insert those guys in here. Well, this is going to be y minus f at x naught is equal to f prime x naught x minus x naught, like that. And so we know that if we take x, this guy right here, well, I'm going to move some stuff around here. So this is going to be y, okay, is going to be equal, okay, so this, the y value, the y value anywhere on this guy, that's this right here, this is y x. Y is going to be equal to f prime at x naught times x minus x naught plus f at x naught, just like that. And if this guy is x and this guy is x naught, then this distance, so if I'm calling this guy, whoops, I wrote those guys in reverse, x, y. So this guy right here, maybe I should actually write them as something else. Well, no, I'm gonna leave him as, I'll leave him as that because it's consistent with the notation here. So this guy is really x, this guy, and so x is equal to x naught plus delta x. So x minus x naught, if you take this guy minus this guy, that's this distance right here, delta x. So y is equal to f prime x naught times delta x plus f at x naught. And y here, okay, y is this height level right here. So this height level, which is equal to this mess, is a good approximation for this height level. The amount of the error is right there. So big picture is we can use, don't get too lost in the symbols here, we can use the tangent line as an approximation to the function, okay, and to the function values for delta x's that are really small, okay. So the y value and this, so this guy and this guy are very close to one another. These guys are real close when delta x is small, and this y value right here, this height value right here, is given by this. So this is close to this value when this guy is close to 0. And that's this right here. Okay, so that's what we're going to be working on.